Continuing on now to part 4, or example 4 of section 4 of chapter 7. Choosing a college can be an exciting and nervous time. You've had that past experience. Emma has finally narrowed down her choices to the top 4. She's also given each school a probability based on certain characteristics, so we're not doing that part. This is already known. So this is what we have here. So these are the universities that she's thinking about. And these are the characteristics and her probability that she would select it. So what is the probability that Emma ends up at either University B or University D? So what we would look at is, what's the probability of B, 10%, D, 35%, and of course percent is out of 100, so in a sense we could just add the 10 and the 35 and get 45 out of 100, and I'm asking another question here. Are these mutually exclusive? Yes, you can't pick to go to 2 colleges, so she's going to pick one. They are mutually exclusive. And we said that. So we're adding our 10 and 35 and getting 45%. So it's nice to have an easy one. Okay, let's take a look at this now. Independent events. Now, events are independent when the results of one event does not influence the probability of the other event. So let's take a look at this. Oh, before we do that, let's take a look at what a dependent event would be, where the results of one event influences the probability of the other. All right, so you'd want to define these. And here we're asked now, determine if the following pairs of events are independent or not. So if they're not independent, then they would be dependent. And these are a little bit challenging. So let's read them over carefully, and then you're going to make a choice. And you'll see how you come out. Event A, eating a red candy from a new bag of Skittles. Event B, pulling a second Skittle from the same bag that is also red. Now, is event A and event B independent, or are they dependent? So write that out. Make a choice. Event B. Let's look at B and then event A of that. A woman is given birth to a daughter. Event B, the same woman gives birth to a second child that is also a girl. So in B over here, are these events independent or dependent? All right, now for C. Event A. Tina is the first woman to finish the 2020 Boston Marathon. Event B. Tina is the first woman to finish the 2021 New York Marathon. Now, as you think of this, again, you're going to ponder, and are these events dependent or independent? Okay, let's check them out. I already looked ahead, so I know the answers. So the Skittles, even though you're drawing them one and then you're drawing another, are dependent because when you took a red one out of the bag, there are fewer red ones in there. So you're taking that first red one out, reduces the overall number. So they are somewhat dependent. Okay. Now, of course, if it was replaced in the bag, the original one, then that would have been independent because you wouldn't have changed the overall numbers. But then you've eaten that first one, that makes it dependent. Now here you're saying it's coming from the same mother. But the event of the birth of one is actually independent of the birth of another at a later time. So, in example B, that would be independent. Now, this is the one I got wrong myself before I looked at the answer. And again, we're here to learn things and to, challenge and develop a better understanding of things. And they describe that here. The thing is, winning a race, you are in training. Winning another race, because of the training and the additional practice and development of skill, they're saying it makes it a dependent event. Now, if I were a lawyer, of course I would argue, then what would reasonable people think? But for this one, we're going with this. Now, sometimes your personal knowledge may give you an edge on determining something, but in other cases you may have to rely on experts. We have the idea, is it a subjective view? Are you clouding it with your own personality and biases? Or is it an objective view where you try to be an equal and fair judge based on just what you're observing? And of course, this is what trials are made of in life. All right, let's go on. Okay, a new rule here now. This is the multiplication rule for independent events. And we say if A and B are independent events, then the probability of A happening and B happening is given as a product. That is, you're going to multiply the probability of event A happening times the probability of event B happening. So this is the rule, the multiplication rule for independent events. You want to put that in your notes. All right, let's take a look at one in practice here. Given a fair die, that's one of the set of dice, has 6 sides, and a standard deck of cards that has 52 cards, find the probability of rolling a 6 on the die and drawing an ace. Well, we might think of this a little bit here before we get started. So for rolling a 6, that's going to be 1 out of 6. Now here, because they're independent events, we're going to have the multiplication rule apply. Now, how many aces are there in a deck of cards? And the deck contains 52. So we could do some cross-canceling, or since we're going to use our calculators, this is going to be 4 out of 312. Put that in our calculator, and we get 0012821. And I believe that's approximation, so we have to put wavy lines there. But again, the multiplication rule for independent events: a fair die, 1 out of 6. An ace, 4 out of 52. Just multiply your numerators, denominators, put that in the calculator, and there you go. And there is your text supporting that. Okay, multiplication rule for independent events. Suppose we have the following breakdown for internal medicine and pediatrics: hospitalist. I believe that word describes people who work in the hospital and at this regional hospital, and the ages of the patients on a given day. So, as we look at this, we're going to get some results here. Now over here, how many hospitalists are we dealing with? Well, we'd have to add these two, and we're going to get 13. And how many patients? Add these 3, and we get 72. So I'm going to repeat this chart on my next slide, but normally they wouldn't have it, but I fiddled with them a little bit, and you're going to, again, take some notes. And I've put there, we can see it pretty well. Let's see, here we go. What is the probability that the first patient treated is over 55 years old and is treated by a male hospitalist at the Madison Regional Hospital? So here we have to look at our data carefully. How many patients are 55 years old over that? And we look here, we see there's 21. So 21 out of 72 patients. And then how many are male hospitalists? 6 out of 13. So that gives us some calculation here. I can move this back up here now. So 21 out of 72. You want to be sure you see where these numbers come from. And the male staff in the hospital, 6 out of 13. They are independent events, so we're going to multiply the 21/72 times 6/13, and they do the math for us here. It's very nice. 6 times this is that, and 72 times this is that, and put that in your calculator and you round off at this. So sometimes it can be a little tedious. What are they asking? Carefully look at your data, pick out what you need, and then show the work. Okay, now we talked about the earlier probability. Now we're going to take a look at what is called conditional probability. And what does this refer to? Well, the probability of event B happening given event A is the probability of event B, assuming that event A has already or will at some point occur. Again, you may have to pause and read this again. And it's written. This is the key point here. The probability of B occurring given A is read as the probability of B, that vertical line is read given A. The probability of B given A. Alright, this is what we call conditional probability. And in some cases you'll have to determine whether you're dealing with this type or the other. Now, the multiplication rule for dependent events, now not independent, but dependent events. Dependent indicates conditional probability. And this is the formula. That A and B would be the product of A times the product of B given A. So this gets a little challenging. Let's look at an example here. Find the probability that from a standard deck of cards, 52 cards, you're dealt 2 cards. The Queen of Hearts, and then a face card. Now, as we look at this, and we'll think about this together as we do it here. How many Queen of Hearts are there in a deck? Only 1. So that's 1 out of 52. Now, is the Queen a face card? Yes. So if you picked out the Queen out of 52, that of Hearts, how many face cards do you have left now in the deck? Well, you don't have 12 anymore because you've picked out 1. So you will have 11 face cards remaining. But now, as part of our conditional, you now only have 51 cards left in the deck. So when you do the multiplication of this, this is going to be 11 over 2652, which gives us an approximation of 0.004148. So this is a dependent event because by removing a card, you now have less cards in the deck, sort of like the Skittles here. There's 1 less red Skittle ball, or whatever in the deck or in the bag. Okay. All right, let's take a look at what the book is going to offer here. And again, dependent events. There's your Queen of Hearts. But now only 11 face cards remaining. So 11 out of 51. So our calculation being this. Now, we have this other example on conditional probability and then one on example 10. Two more examples. They're going to take a while. So we're around 20 minutes. So this will complete part 2. And then we'll have one more part, and that'll complete our flipped classroom lecture series.